splitting field, it says that if K is the splitting field of polynomial f of x, and we have some another splitting field of this polynomial f of x, so that means we have f of x which is present in f of x in the polynomial field f of x, then according to this, if E is the splitting field, if K is another splitting field, then we say there exists a mapping or an isomorphism from E to K such that it acts as identity on F. So this mapping is identity mapping which is also an isomorphism. So that is what we are to prove in this theorem. So here let us see this. It says that we assume K bar to be the algebraic closure of K. K is given to be the splitting field of F. So there is, for every field we know there is an algebraic closure. So this is the algebraic closure for K. So we say this K bar be as an algebraic closure of K. If K bar is algebraic over K, that means K is also algebraic over K. This is given to be algebraic over K, and this being splitting field is algebraic over K. That means this would also be algebraic over A. Why? Because we know that algebraic extension over an algebraic extension is an algebraic extension. So K bar is algebraic over F. So from here we say that whatever is the closure of this field F, that is represented by F bar, that is equal to K bar. So the closure of K is equivalent to the closure of F. The next thing we have to show that what about this mapping sigma from E to K. So here we shall prove this thing. To prove that the mapping sigma from E to K is an isomorphism and it is also an identity map. So in this case we see E as an algebraic extension of F. Now according to this result that we have studied, that whenever we have some field E and some field F, we have some field F, E be its extension field, and we have some field K here, right? So if E and F be fields and sigma from F to E be an embedding, this is given to be an embedding, then there exists a field K such that F is also a subfield of K and sigma can be extended to an isomorphism of K onto E. So this could also be extended to another mapping which is also an identity mapping, and this now becomes an isomorphism. Isomorphism, that means it is 1 onto and homomorphism. And this mapping is given to be embedding, that means it is 1 and homomorphism. So this is the result. It says that if you have some extension field where this mapping sigma is defined and it is an embedding, that means these two conditions are satisfied, then we can extend the field K, we can extend this mapping to another mapping such that this field is an this mapping forms an isomorphism. So this is in accordance with this previous result that we have studied. So here, to prove that the mapping is an isomorphism or it is an identity map, so for that what we do, as E is an algebraic extension of F, therefore there exists an identity map from F to F that can be extended to an embedding E to K bar using the following result. So we have the situation, we have F from F, the identity mapping, which is an embedding, right? We have some extension E of K. So we are saying we can extend this mapping to another mapping sigma such that from E to K bar we have isomorphism. So this is what we have said until now. So if we assume that the polynomial is given by this a0 plus a1x plus up to an x raised to power n, which is some polynomial in this field f of x, and all the coefficients a0, a1 up to an, they are in this field f, Then we can define another mapping. We can set f sigma x, which is related to this sigma, using the same polynomial where now the coefficients have been replaced from a0 to sigma a0, from a1 to sigma a1, and so on up to an to sigma an. So this is given to us. So we assume another polynomial f sigma x, which is defined to be like this. So then we say this mapping and this mapping is exactly the same. How? Because we know sigma mapping was an identity mapping. If this was an identity mapping, so that means sigma of a0 is exactly equal to a0, sigma of a1 is exactly equal to a1, sigma of an is exactly equal to an, and so on. So that means a0 is equivalent to sigma a0, a1 is equivalent to sigma a1, and so on. An is equivalent to sigma an. So this is what we have, right? So this is what we have. So according to this thing, we said f sigma of x is equivalent to f of x. Now we have to show that E is the splitting field for this polynomial. So this is given to us. E is the splitting field of this polynomial. So that means this polynomial could be written as the linear factors into the linear factors, where alpha 1, alpha 2 up to alpha n, they are the roots of this polynomial. And because we have fx equal to another polynomial f sigma x, so that means we can write this fx as c as such, x minus, instead of this alpha 1 we now write sigma alpha 1, instead of this alpha 2 we now write sigma alpha 2. Why? Because this mapping is an identity mapping and sigma alpha 1 is equivalent to alpha 1, and so on. So this is the polynomial that we wrote. Moreover, this polynomial has splitting field E. It is also given this polynomial has splitting field K. So we can also express this polynomial into linear factors where all the coefficients are in K. So this polynomial becomes x minus beta 1, x minus beta 2 up to x minus beta n. So that means this set of all the roots sigma alpha 1, sigma alpha 2 up to sigma alpha n, and the roots beta 1, beta 2 up to beta n, they both form the roots of this polynomial. These one are in E, these one are in K. So that means, and moreover they both are equal because we have a unique factorization of this. So that means whatever is the root here would be the root here. So these two sets are identical. They are in E, they are in K. So we can say this K is nothing but the field F where all the roots in K have been adjoined to it, beta 1, beta 2 up to beta n. Moreover, because these two sets are equal, so that means beta 1 is equivalent to sigma alpha 1, beta 2 is equivalent to sigma alpha 2 up to beta n, which is equivalent to sigma alpha n. So now, because sigma is a homomorphism, it preserves this structure. So we can take this sigma common from all these terms. So we can write this to be sigma of f of alpha 1, alpha 2 up to alpha n. And what is this thing? This is the splitting field, because E was also splitting field of f. So it was f of alpha 1, alpha 2 up to alpha n. So this is sigma of E. So we have identified K as equivalent to sigma of E. So moreover, this mapping was an identity mapping. So this is automatically 1 1 on 2 and is a homomorphism. So that means we say the mapping sigma is an isomorphism of E onto K. So I hope this one is clear.